Hi, chemistry students. This is your introduction or continuation of what we've been talking about, gas laws. We talked about gas laws in our session earlier this week, and now we're going to go into specific gas laws and what they mean. So we're going to start with Boyle's law, and gas laws are going to relate those five things that we talked about earlier. Let me go back to those real briefly. The five things that we're going to be interested in when we're talking about gas laws are volume, that's how much space the gas takes up; temperature, how quickly its molecules are moving; the number of molecules or moles of the gas; and its pressure. So I guess that's four things. My bad, I can't count. So we are going to start by relating two of those things in each of the laws that we talk about. So in Boyle's law, he's a good-looking guy, hey? In Boyle's law, we are going to relate pressure and volume. So this little fish-looking symbol right here means that it's proportional. They're not equal to each other, but they have a relationship such that as one goes up, the other goes up, or one goes down, the other goes down. So they are inversely proportional, meaning the exact opposite. If one goes up, the other goes down. So if I increase the pressure on a gas, the more I push on it, the less volume it takes. So if you could imagine a syringe, on that syringe, I could push on that syringe, and the amount of space that the air takes up in that syringe would decrease. And we can see an example of that, or the law that gets written from that, before the example, is the pressure and volume of the first situation are equal to the pressure times the volume of the second situation. Units are not important for this so long as the units are consistent, meaning that pressure could be in atmospheres or pascals, but as long as it's the same on both sides. And the same thing with volume, could be in liters or milliliters or cubic centimeters, and it doesn't matter as long as it is the same on both sides. So you're looking at one scenario, this is what's happening in the first situation, and this is what's happening in the second situation. So for the example of my syringe, if I had a certain amount of gas in a syringe and I was pushing on it at a certain pressure, the volume that the syringe would take up would be the situation one. I increase the pressure, now I have a new pressure and I will have a new volume, and then when you multiply those two together, they will be equal to each other. So we actually see this in using a bike tire pump, if you've ever used one of those. What you do is you push down on the pump, and as you push down on the pump, you are decreasing the volume of the space the air in the pump is by pushing it down, as you can kind of see in this scenario up here. And that's increasing the pressure, which causes the air to be pushed into the bike tire. So you continually do that, and you can get your bike tire pressurized so that you can go for a bike ride, which would be a great thing to do during quarantine right now if you have some extra time. So that was Boyle's law. Boyle's law relates pressure and volume. So as you're kind of taking notes or kind of noting these things, Boyle's law, P1V1 equals P2V2. Then we have Charles, also a nice looking guy. And Charles said, let's look at not pressure and volume, let's keep everything else the same, but look at volume and temperature. And again, that little fish sign means proportional. They are directly proportional, meaning that whatever one does, the other does the same thing. So if the volume, or if the temperature is probably the easier thing to talk about changing, temperature goes up, that's going to make it take up more space. An example of this that I have told before is that when my kids were little, my husband's birthday's in February, and we went to the dollar store and they picked out birthday balloons for him, and they were super excited about their helium balloons that they were going to give to their dad, and we walked outside and the helium balloons crunched, and they were little teeny small, and I don't remember if it was Ezra or JL, but one of them started crying because they're like, my balloon is broken. But that's not true. What happened is the temperature decreased, and if the temperature decreases, the volume is going to decrease as well. And you can think about why that's happening, because we talked already about the kinetic theory of gases. And an ideal gas, the molecules are constantly moving and bouncing off of each other. And so as they move and bounce off of each other, the temperature goes down, makes them bounce off of each other less often. That makes them be able to be closer to each other. And as they're closer to each other, they take less volume. The formula for that then is that volume over temperature equals volume over temperature. and the news situation. So this would be the balloons in the dollar store when the temperature was high, the volume was high. Then we take the balloons out of the dollar store into the February Wisconsin air, and the temperature goes down. So therefore the volume is going to go down to keep that relationship equal to each other. And you can see that if we were to look at a balloon in ice water versus a balloon in hot water, the balloon in ice water is going to be smaller than that same balloon in hot water. So now we have two relationships. We're going to have one more. So the relationships we've looked at so far were the relationship for pressure and volume. Then we looked at temperature and volume with Charles' law. So you can imagine that the two things that we haven't talked about yet are pressure and temperature, and that's Gay-Lussac's law. So this is Gay-Lussac. You can see we're getting a little bit closer to modern times. And Gay-Lussac says that they are, again, directly proportional. So you can kind of imagine that the same thing happens with my kids' balloons. If they have a high temperature, those molecules are going to be moving faster. As they move faster, they have more collisions with the surface of the balloon, causing that to be more pressure, because that in essence is what the pressure is in a gas, right? It's the number of times that the gas molecules collide with the side of the container. And so therefore, when the temperature outside went down, those gas molecules inside their helium balloons were not moving as quickly, so they weren't pushing as hard on the foil balloon, and therefore the foil balloon did not have as much pressure inside. And that comes all together. So that's three gas laws that take all three of those. You can notice that the one variable that we have not talked about is moles, and we will not talk about that just yet. We can put all of these things together. So you don't have to remember each of these separately, but you can just remember them all together. So we have that combined gas law. So the combined gas law looks at the pressure, volume, and temperature in one situation. Then that same gas in a novel situation we can compare. So you can actually look at this and you can see that you can get all three gas laws by covering up one of them. So if we get rid of temperature, which law is that? You were right, Boyle's law. If we take the combined gas law and we get rid of pressure, which law is that? Charles' law. And if we take it and we get rid of volume, that is Gay-Lussac's law. So that's really what you need to pay attention to, is this entire thing, and just know which one is held constant, because in each of those individual law, Boyle's, Charles, and Gay-Lussac, one of the variables is held constant. So look at which one is going to be held constant and then make your, you can know the three gas laws from that without having to look at it. So you might say, how am I going to deal with real life using these combined gas laws? They're useful. They're useful for talking about a helium balloon being taken outside for a dad's birthday in February. They are useful in talking about how much pressure is on a syringe that's filled with a gas. They're useful in looking at the amount of space a balloon is going to be taking up if it's heated, and things like that. But what they're not very useful for, even though we talked about the bike tire, is what if I say to you, I have a flat tire? What am I going to do about the fact that I have a flat tire on my car? Well, what I'm going to do is I'm going to put more air in it, right? So if we look at these laws, what we could say from looking at the combined gas law is, if I don't have enough volume, what could I do to make the volume in my tire higher? Well, I can either decrease the pressure. So you're driving down the road and you have a flat tire. You need a bigger volume in your tire, so you can just decrease the pressure of the whole universe, right? Obviously not. The other thing that we could alter here is we could alter the temperature. So if I need a bigger volume, I'm going to need to have a bigger temperature. So I could just heat up the entire universe, right? Well, obviously that's not the case. So there's something else that we haven't talked about that we need to talk about, and that is Avogadro's law, or hypothesis. Avogadro, we know already from Mole Day, right? We learned him. He came up with the idea of a mole, and he applied that to gases. So he said that if we have the same temperature and pressure, we can have a relationship between volume and amount. So volume and amount are directly related. The more stuff we have, the more space it takes up. That's kind of common sense. So That's what Avogadro said, and we can put that in together, and that gives us what we're going to do when we have a flat tire. We're going to put more air in the tire. And so therefore, we have Avogadro's law being added to the laws that we already have. That gives us what we call the ideal gas law. So now we have relationships with P, V, T, and N, and we can put them all together. I'm not going to go into a lot of time, but you could look at this derivation. All these things are proportional to each other. When we want to turn a proportionality into a equal sign, we have to add a constant. That constant is R, the ideal gas law constant, and that leads us to the ideal gas law, sometimes called Pvnert. So Pvnert says that pressure times volume times equals the number of moles times the constant, which we'll talk about in a second, and times the temperature. All temperatures, which we talked about earlier, in any gas laws need to be in what units? Yes, in kelvins. We can't do them in Celsius because we can't use negative numbers when we're doing proportions. So we need to use kelvins that has no negative numbers. So this brings together all of the gas properties. We talked about how to derive it. And this is an equation that you must know. So make sure that you know this, as well as the combined gas law, but particularly this one. So P is pressure, V is volume, T is temperature, N is number of moles, and R is that constant. That constant can be looked up. I would give it to you on a test or a quiz. I tend to like to just have one and always use it. The only thing that you need to pay attention to is units. There are others given in your book on page 364, but 0.0821 if you use liters for the volume, ATMs for the pressure, moles for moles, and kelvins for temperature will be something that works really well. So this might be the easiest one to just write down and keep track of and use. So we can do a problem. It says that there's an 18-liter container holding 16 grams of oxygen at 45 degrees Celsius. What's the pressure in the container? You can notice that this is not a combined gas law problem because of the fact that we don't have two scenarios. It's just this is how it is. In a combined gas law or Boyle's or any of the other ones that you've worked with, it was like it used to be this way and now it's this way. It's like two scenarios. That's the difference. So the pressure is what we're looking for. We have the volume. We have the ability to easily get the temperature into kelvins. We just need to do the conversion to get our grams to moles, which we're all very good at. Once we have that, we can put it in and we find out that it's 0.73 atmospheres. Feel free to pause the video if you want to try that on your own first. That is a great idea. So as I said, we want to look and see which one to use. If there's two situations, we're going to use the combined gas law. In that situation, units are not that important. They just need to be the same on both sides. If we have one situation, we need to use the ideal gas law. Then units do matter. The way to tell if they match is if they match the constant that you're using, and then you'll be all set. So hope you enjoyed, and obviously I will be around to answer any questions you have. Just drop in office hours. See you later.